Hello, welcome everybody to the second lecture of this series. So today I would like to have a short lecture on classification of mathematical models. This is necessary because, as we discussed in an earlier lecture, there are different frameworks of models available. I mean here, mathematical frameworks, and you have to choose these frameworks carefully so that they are adapted to the problem you want to solve with them. The issue is, of course, that you need some kind of equivalence, as we discussed it earlier, between the modeling structures and the mechanisms which we have discussed that are there or that are present in the empirical system to which we apply the mathematical model. So let's talk about this classification today. First of all, I would like to say a few words about typical model components, and this is somehow universal throughout all frameworks you can possibly have in mathematics. So there are, first of all, there is this issue which we will discuss a little bit in more detail at the end of the lecture, that mathematical models are, of course, a very compact way of describing a real-world problem, and that is, I would say, that is really the main point why mathematical modeling is so dominant in the sciences. Actually, not only today, but it was always throughout the history of science. It was always like that. So the compactness of mathematical descriptions is really what makes them attractive. So what is usually a mathematical model? Well, it is more or less mostly a mathematical equation or a set of equations that you use for the description. And there, in such equations, there will always be the most important part, and these will be the variables. As we will discuss later in this lecture, variables, of course, are the main ingredients of the mathematical model that are then more or less even one-to-one connected to real-world empirical observables. So here you have the main connection. And as the name suggests, of course, the variables will be varying. That means, they will have different values, and that will describe either a prediction, so what will be the future states of a system, or it can also be that you have to compute the variables in a static model such that they exactly fit what the real world empirical observables are, so that you reach this kind of equivalence relationship between model and empirical world. Now, of course, there are other things in the equations, and these are the parameters. This is the second most important ingredient. So in mathematical modeling terms, every mathematical model, of course, has parameters, and if not, it can be parametrized easily. That means parameters have a special function in mathematical models. Well, usually they are thought to be the things that are not varying, so that are fixed. So it is very often loosely connected to what you would call, maybe, according to Kant's interpretation, a priori knowledge about the system. Or it can also be, as we discussed in the scientific cycle, it can be something you have measured before validating the mathematical model. Excuse me. And yeah, a good hint for the people who know that is that parameters are also used, for example, in statistical modeling to vary the fundamental properties of the model without changing the model itself. In this sense, you can think of homotopy theory. So two, let's say, possible incarnations of a model can be connected by a smooth path, and then in model space, and then the homotopy parameter would tell you, how far you are from one end of the model in this path, and how far away you are to the other extreme, ending up in the other model. So parameters are, well, let's say the second most important ingredient of such a model. So let's go to the third part. So whatever you have in the first two components, so parameters and variables, you will somehow need to describe relations. So relations, generally, the whole area of mathematics that deals with relations is immensely important for a mathematical model. That's why we will start now to discuss graph theory. That is the most basic mathematical theory you can have that incorporates relations, but it will go much further. You can also cite here, for example, algebraic topology, because, for example, simplicial complexes are also describing mathematical relations between objects. So relations will be very important, and they will also play a crucial role, for example, to discuss possible feedback loops, one of the main features of mathematical models. The next thing I would like to discuss today is a very important distinction in mathematical modeling, and that is top-down versus bottom-up modeling. It is as follows. We have already introduced basic entities. That is usually a kind of thought experiment first. It is also, again, related to a priori knowledge. So you think that you have a basic entity in your empirical system, and that is something you don't want to divide further. So in that sense, the basic entities are also something like the elementary particles of the system, so they cannot be further divided. You see by that example that this is very old, let's say, also pre-science thinking. So the idea of atoms, of course, already appears, for example, in the Greek world, in the ancient Greek world. And you have exactly the correct idea when you think of these basic entities of the empirical system as atoms which are not further divisible. So this can be, in a human society, this will be something like people, individuals, and indeed in a physical system it could indeed be elementary particles. Now, now what is the difference between top-down and bottom-up? Let's maybe go to the next slide. Well, the basic idea is that in a top-down approach, you are not so much first concerned about the most basic entities as we just discussed them in the empirical system. You want to aggregate variables, so you are not talking about, for example, different types of elementary particles. You are talking right away about a field. That is a notion from physics. So a field, for example, can be something like a gravitational field, and that gives rise to equations, or you can possibly have equations which then do not describe elementary particles, but they describe all kinds of gravitational influence by any mass that is in the system. And so they don't care about about the most basic description of the system. So they such models like the Einstein field equation go to the top. Usually what you do is you guess how the equation for the field should look like in order to explain empirical observations. That's exactly what Einstein did. And then you derive properties further down which more basic entities in the system have to satisfy, because, for example, these top-down models at the top of the modeling effort give, for example, certain conservation laws, which then you have to satisfy in all lower descriptions of the system. Now you can also go the other way around, so bottom up. And the idea here is indeed to go right away, not right away go to the basic entities of the system, and then you aggregate, or you aggregate then from their properties. So that is a very typical approach, for example, in stochastic processes. And one of the best papers is here from Einstein. He derived the diffusion equation by using a particle approach in his famous paper, and for that he also got the Nobel Prize. Interestingly enough, he got the Nobel Prize for that kind of bottom-up modeling. So Einstein is one of the few people I know that have done such amazing modeling work in both fields, so top-down and bottom-up. Let's skip this slide for the moment, but I would like now to go to an illustration of the top-down and bottom-up modeling. And here you see the two approaches side by side. So here, for example, you have the bottom-up approach on the left, and what you have here is indeed, so as I said, you start here with the basic entities. This kind of graphics has two dimensions. One is the hierarchy, so the basic entities are at the lowest level of the system, of the empirical system, and then you have these different bars. They are indicating description levels. So you see that at the lowest level you have the complete information, so you try to make a model of all basic entities you have in the system and their properties, and then by aggregation you might have a little bit a more compact mathematical model, and so the description depth, so the width of this line is decreasing the more you do aggregations, but you climb up, on the other hand, this ladder of scales. So you can go from very, very fine scales of the empirical systems to more larger and larger scales. So In contrast to that, you have this situation here to the right. Here you do exactly the opposite, as I explained with the Einstein field equations. So you go with a very you go with a detailed description. You start with a detailed description of the aggregated variables. So that would be, in this case, the starting point here. And then you go to finer and finer scales. So you use the implications of the macroscopic scales, that's how they are usually called, here at the top level to finer and finer scales. And you derive implications for these entities until you reach the scale on which the basic entities are acting. Okay, now let's go further to model classification. So after having discussed this kind of two basic modeling approaches, I would like now to tell you a little bit about pairs of model classification. So these are thought as always being two extremes a mathematical model can satisfy. So the first distinction is between static and non-static models. Here you see this is also the basic separation of part 2 of part 1 and part 2 of this lecture. So this is important. Well, the difference between static and non-static model is that usually, in the static description, you talk about mostly about the relations of the system components to each other. So what are these relations to each other? Of course, that can be that can depend on whether you have the top-down or bottom-up approach, which defines then what your variables in the model would be. But you are not concerned, for example, about time evolution in the static description. So in the non-static description, obviously you think about the dynamics of the model. So you have you should not necessarily think about time, but of course mostly about time. In any case, you have a set which is linearly ordered, and so you have different points in time in parentheses, which can be compared to each other, and you try to describe how from one point in time to the next, your system is changing. That would be the non-static description. Sorry. So let's go to the next slide. And here you see another distinction to classify models, which will also become important in the next lecture on complex systems. So you have the pair linear versus nonlinear modeling. I would like to describe this a little bit in terms of ordinary differential equations, because that will be the most relevant kind of explanation I can give you here for this course. So if you remember how the situation for ordinary differential equation was, then you have the following. So for a linear ordinary differential equation, you can construct the whole set of the solution of a set of equations by composing in a linear way the solutions of more elementary equations. So you know that this goes by separation of the eigenvalues of the matrix that defines the right-hand side of the ordinary differential equation. So this gives you a full global description about any possible dynamics the system can have. And you can imagine, if you really think your real-world system is of linear nature, then it will be very, very easy to parameterize your model, because you really know that your structure is finite. You have a global a priori knowledge about all possible movements the system can make, and therefore it will be very, very easy to parameterize such a model. Now go to the nonlinear situation. In this case, it's much, much more complicated. You have nearly no chance to have any global information about the system. You will only have local information, and that is because you can linearize. That is a very important feature of the model, of the nonlinear system. And yeah, so you can, in this case, you make use of linearity in a local area of the state space of your system. Okay, now let's go to the next distinction, and that is discrete versus continuum. And that's a very important distinction because discrete mathematics is so much different from continuum mathematics. And of course, as we have already, for example, discussed in the pair static versus static versus non-static, mostly, for example, graph theory is a discrete mathematics type, so this kind of descriptions is important there. On the other hand, you need, for example, for many things related to dynamical models, you will have to have a continuum approach. For example, you need to have the notion of a differential, things like that. Now let's go to deterministic versus stochastic. This is also an immensely important distinction between mathematical models. Historically, because mechanics was so important in the, let's say, in early science, deterministic modeling was, of course, the choice, and it was a whole mindset, and many people have struggled to go away from deterministic modeling. For the very famous example is again Einstein, who was opposed to the interpretation of quantum physics, as you might know, in his early days. So yeah, so deterministic thinking is very often related, to ideas that the universe does not gamble, things like that. But in reality, most of the systems we know nowadays have a stochastic nature. So that is more and more observed, that in reality stochasticity is really needed to describe a system. And then the deterministic systems usually only appear because they are, let's say, simplifications of stochastic model. For example, by doing ensemble averages, things like that. Yeah, this slide I would like to skip. You can read it later in the slides I provide, but they are also important distinctions for model classification. Now let's go very quickly to the most important point of the lecture, and that is Occam's razor. So we have now talked about model classification. We have introduced these pairs with which we can classify mathematical models. But now the question, of course, arises: you have this full choice in an abstract model space. Which framework do you use for your model? Where is it located inside this inside these pairings? So is it more stochastic? Is it more deterministic model? Well, the thing is, generally there is a scientific principle which is known as Occam's razor, and that is if you have two models of the same complexity, then you should use the simpler model, so the one with less complexity. The reason for that is if you do so, you have the possibility, you exclude more hypotheses in the world, and therefore the simpler model has more scientific value. So the Occam's razor is one of the most important scientific principles, or it is actually the most important scientific principle you have. But the question, of course, is how do you measure model complexity, or how do you decide that one model is simpler than the other one? That is actually sorry, excuse me. That is actually a very important question. There are different answers to that, obviously, and it will be a very important discussion for science in the future. But one thing you can, for example, discuss is algorithmic complexity, which is mostly related to Kolmogorov, who introduced this concept in the 1960s. And it is a little bit like that. So you look at the mathematical model, you attach information to each of the ingredients of the model. So for example, if there would be a number in the model, then the bit string attached to display this number would be exactly what I mean by attaching information to an object in the mathematical equation. So you do that for all kinds of ingredients as we discussed them before. And then you introduce a compression algorithm. So you have an abstract computer program that can exactly reconstruct all of these strings of information, so the binary strings of information you have attached to each mathematical object. And this computer program is able to reconstruct that. So in other words, this is a real compression. And the length of this computer program then is defined as the algorithmic complexity. And this would give you, at least in principle, a way to decide which model is simpler than the other one. So let's go to the summary. Today we learned about basic building blocks of mathematical models. We discussed the difference between top-down and bottom-up modeling. That is very, very important. We learned about static and dynamic models. We discussed the difference between linear and nonlinear, discrete and stochastic models. Again, very, very important distinctions to classify mathematical models. And we discussed a little bit how model complexity can be used to decide which models are simpler than the other one. And we discussed the most important scientific principle of all, which is Occam's razor. So yeah, goodbye, and I hope we see us then at the next lecture.